Thank you. Thank you for coming. This is late afternoon, so I really do appreciate your presence here. And also, this is a very special occasion. I really think that it's fantastic to celebrate birthdays. So I wish all the best to Gabor, Ted, and also Andre on their 70th birthday. Also, I want to thank them to publish important work that helped to progress discrete geometry a great deal for many years. Last but not least, all three of them supported, in general, the discrete geometry community a great deal. Partly for that, I remember that I was invited. My first trip to Canada was in 1985. And my host was Ted Bystrisky, and that time I was much younger and highly appreciated that invitation. So thank you to all three of you. Now this talk is going to celebrate another birthday, which is not so lucky. I would love to see the conjecture vanish, or I could put it in that form that I do not want to wish many returns to this conjecture. And as the slide will show here, this conjecture goes back to a number of years. I will just start with some brief overview of the conjecture. And if you would like to know more about it, there is a chapter in this book that discusses it. So I need a minimum notation here for the conjecture to state. So it will happen in the d-dimensional Euclidean space. So the length or the norm is the usual Euclidean norm. If we take 2 points, pi and pj in that space, and the norm of this difference vector means the distance between those 2 points, I will need to talk about point configurations. So boldface P here refers to a point configuration consisting of points P1, P2 up to P capital N. And it is convenient to say that the point configuration Q is a contraction of the point configuration P if the corresponding distances in this points configuration Q are smaller than or equal to the corresponding distances in the point configuration P. In other words, the distance between Qi and Qj is upper bounded by the distance between Pi and Pj. If that happens for all ij, then we say that Q is a contraction of P. Another method that I need here is I need a notation for the ball centered at, say, point Pi, having radius Ri, and this is the notation B. These of Pi Ri stands for the ball. Now then, after this, we can put forward the conjecture. So this was raised in 1954, 55, actually 2 different people. We know Martin Kneser, at least from that point of view, that he had serious reason to put forward this elementary conjecture. I don't know the relevant part from the point of view of Poulsen. The pictorial description is this. We have a point configuration, P. We start with that. And these points will serve as center points for balls of not necessarily same radius. So P1 is center of a ball of radius R1. P2 is a center of a ball of radius R2, and so forth. And then we contract the center points, but we do not touch the radii. Radii are kept fixed. And the conjecture says that if you contract the point configuration P onto the point configuration Q, then the volume of the union of the balls changes monotonically. In other words, if I contract P onto Q, then the volume of the union of the balls decreases. A rather natural conjecture. There is a close relative to it, which was raised a number of years later. And, I would say that Klee and Wagon are the two people who actually put forward this conjecture for intersection of the bores. So the setup is the same as before. We contract the point configuration P onto Q, and then the claim is that the volume of the intersection of the bores increases under arbitrary contraction. This is where it was published. This book is a good source for that. Now, I want to say some words about the status of the conjecture. So there will be some statements here where we'll start with continuous contractions, because the conjecture is proof for continuous contraction. Now, the notion of continuous contraction is exactly what you would imagine, but for safetyness, I put it here. So imagine that we have the point configuration Q as a contraction of the point configuration P. Then there may or may not be a continuous motion of the point configuration P, labeled by P of t, such that when we look at the distance between Pi and Pj, then this distance is monotone decreasing over the interval 0, 1. So we just normalize the interval to 0, 1. So if this holds for all I and j, then we say that the contraction, which is represented by this continuous map P of t, is a continuous contraction. Okay, then it's not hard to see that not every contraction you can obtain as a continuous contraction. So this is a special class of contractions that we are looking at here. Now, the theorem is due to Chikos. This was quite some achievement, because the story started with a very nice paper of Bolobás in the late 60s, when he proved the Kneser-Poulsen conjecture for continuous contractions in the plane. And then some years later, Capoelas proved it for intersections. So the Bolobás paper is for union, Capoelas for intersection. And Chikos' theorem actually not only state that the Kneser-Poulsen conjecture holds for continuous contractions, but it does give a formula. And whenever we see such a nice formula, that's very impressive. This tells how we prove it. So the formula here relies on the following. So on the one hand, we have a smooth motion of a point configuration. And, well, there are two cases. We take union of bores. We take intersectional bores. And then there is an underlying structure here. On the left, you see union of circular disk here. And the underlying structure is the closest point Voronoi diagram. Each cell is truncated by its own disk. On the right, we see the farthest point Voronoi diagram, and then truncated by the relevant bores. And his formula says that if we are interested in the derivative of the volume of the union of bores, we just look at this sum, where each term is a product of two things. There are walls here, so if I look at, say, these two cells, for instance, there is a common wall, codimension 1 set, which has some measure, so that volume we take and multiply it by the derivative of the distance between the center points of the cells. So if we have a continuous contraction, then, of course, all these derivatives are non-positive. As a result, this sum is non-positive, so that means that the volume of the union decreases. So a related formula holds here for the intersection. Now, another fact that is known about this conjecture is on this slide. The conjecture is proved in the plane without any restriction on the type of contractions that we are looking at or investigating. So the theorem in this form just says that, well, indeed, in the plane, if we contract a point configuration P onto a point configuration Q, then, as it is claimed in the Kneser-Poulsen conjecture, the area of the union of the disk decreases, whereas the area of the intersection of the disk increases. Well, actually, the theorem has a more explicit form where we see three parts, and these three parts give the way the conjecture is proved in the planar case. So just very briefly, we'll show it here, just to indicate what kind of idea we use here for the proof of the planar result. The first thing is that we have analytic contraction in action here in this first part of the theorem. P of t is an analytic contraction. And when we look at, say, a union of balls, each ball contributes to the boundary of the union along some set which we label by F sub I. So F sub I is the contribution of a ball to the boundary of the union, which has some which has some surface area. We put it down and weight it with the reciprocal of the radius of the actual ball. And in this way, we get a weighted surface volume. So this first part says that this weighted surface volume exactly has this monotonicity property that if we take an analytic contraction, in case of a union, this decreases. In case of the intersection, increases. This is part A of the theorem, and it holds in all dimensions. So there's no restriction on the dimension here. The second part is a pure luck. It's a lucky circumstance that if we restrict the center points to lie in a codimension 2 subspace, in other words, here you see capital L showing up for the subspace, codimension 2 subspace, which contains all of our points. PI's lie in that subspace. Then this weighted surface volume actually means something very good to us, 2-dimension lower. Namely, if I take a ball centered at PI and intersect that ball with my subspace L, then I get a ball of lower dimension, 2 dimensions lower. And, the volume of these of the union of these lower dimensional balls can be expressed has a close connection to the surface volume, weighted surface volume. So this is part 2 here. And part 3 says that this is often called as a leapfrog lemma, which says that if Q is a contraction of P in dimension D, then in higher dimensional space, in dimension 2D, actually there is an analytic contraction in 2D that maps P onto Q. And so here the magic dimension is 2D. And if you put these three pieces together, for D equals 2, you get the conjecture, Kneser-Poulsen conjecture, because D plus 2 is equal to D for D equals 2. So it seems a pure luck here. So somehow everything fits together for the 2-dimensional case. 2 corollaries I want to put forward. The first just says that, well, really our method actually is high dimensional. So if we know that Q is a piecewise analytic contraction of P in D plus 2-dimensional space. So we start with 2-point configurations in D space, Q and P. And if Q is a piecewise analytic contraction of P in this high dimensional space, then the conjecture holds in D space. This is one corollary. The other is connected to a paper of Gromov, in which he actually investigated this conjecture in spherical space. And as a result, he proved the Kneser-Poulsen conjecture in D space up to D plus 1 balls. We could, replace D plus 1 by a somewhat larger number, D plus 3. So in D space, the conjecture, the Kneser-Poulsen conjecture, holds up to D plus 3 balls. That's what I put here. Now, what else should I mention here? There is this very nice, relatively recent paper, well, actually quite recent, 2013, of Igor Gorbovitsky's, which says that one could shorten the claim in this form that the Kneser-Poulsen conjecture holds for large equal radii. So his theorem says this. start with a contraction of P onto Q. Then there exists a magic radius R0 such that if you draw balls of radii R around the points, and R is at least as large as this R0, R0 actually depends on the point configurations P and Q, then the conjecture, Kneser-Poulsen conjecture holds. So really, if P and Q are given, then you can come up with an R0, and if the radii of the balls are chosen such that they're larger than R0, then the conjecture holds. Now, what else? One more matter I should mention here. This is a short detour. So there are, of course, a larger number of results, partial results known. One of which is this, that actually this we got just because we really went after Grommel's idea to investigate this problem in spherical space. So it turns out that in any in d-dimensional spherical space, this Kneser-Poulsen conjecture holds for all for closed hemispheres. So if you start with a finite system of closed hemispheres, in other words, balls of radii pi over 2 in spherical D space, and rearrange them such that the pairwise distances decrease, in this way we generate a contraction, then it turns out that the volume of the intersection increases. Okay, so this is a short sort of description, I think, what we know roughly about this conjecture. And this is the 62nd birthday of the conjecture that we celebrate. And I said at the beginning I would not want to wish many happy returns to this birthday. And so we tried again. So this is a recent adventure that we did with Martin Nassoudi, and as the title says, we here prove the Kneser-Poulsen conjecture for uniform contractions. So the notion uniform contraction comes from Peter Pivovarov. He introduced this, and we have to thank him to come up with this notion of uniform contractions. And before I state the theorem, I need one little technicality here. I do want to use intrinsic volume for the statement, so this is just a brief reminder. Probably most of you know, nevertheless I put it here, that if we use the Steiner formula, we can conveniently introduce these coefficients for this polynomial, which is a polynomial in terms of the radius of the outer parallel domain. And these are called intrinsic volumes. And these intrinsic volume is just a volume. D minus first intrinsic volume up to this constant is the surface area, and so forth. The first intrinsic volume is just a mean width. Now, so then one other matter I will just keep that. So here we go. Notion of uniform contraction. What is a uniform contraction? It is a contraction, but a very special type. So we take Q as a contraction of P, but we assume that there is this separating value lambda in the middle that separates the pairwise distances from the point configuration Q from the pairwise distances from the point configuration P. In other words, the diameter of the point configuration Q is upper bounded by lambda, and the smallest and non-zero distance in the point configuration P is lower bounded by lambda. If there is such a lambda, we say that Q is a special contraction of P. Q is a uniform contraction of P with separating value lambda. Okay? So then the theorem here says that, well, in fact, we can state a bit more than it was stated in the Kneser-Poulsen conjecture in case of intersectional balls. So imagine that Q is a uniform contraction of P with separating value lambda. And then we draw unit balls around our points, and we take their intersection. The conjecture, Kneser-Poulsen conjecture, says that the volume of the intersection of the balls should increase. Here we state more. Regardless what intrinsic volume you take, that increases as well. Unfortunately for the union, this business of intrinsic volume is more complicated. One could introduce intrinsic volumes of for the unions of finitely many balls, but we could only prove the monotonicity of the volume here. So this is the kind of issue that showed up several times in different publications, that somehow, although from certain distance intersection and union seem similar, there is a chance here that the conjecture will eventually end up behave somewhat differently. Perhaps for intersections one can hope for better results, such as the one which is stated here. And for unions one should be maybe more careful. Maybe for unions the Kneser-Poulsen conjecture is more delicate. Perhaps there is a chance that it's not true for unions. Nevertheless, Gromov's feeling in that publication was that they are similar, at least in spherical situation. I do not want to talk about the proofs of this. The reason is this. The proof of this result makes use of the Brun-Minkowski inequality, and as such is very much Euclidean proof. And because I started with this short tour on the status of the conjecture and ended up with this spherical result on closed hemispheres, I want to continue with the aim of proving Kneser-Poulsen type results in spaces of constant curvature, in spherical, hyperbolic, and Euclidean. So we have to, for that reason, if we want to generate a similar analog result in spherical space and hyperbolic space, then we should not really follow the method of this theorem, which is, as I said, based on the Brun-Minkowski inequality. So what I want to do here is to generate a result. Want to look at the case of intersection of congruent balls, contract the center points in uniform fashion. So I will look at uniform contractions in spaces of constant curvature. And we want to prove the Kneser-Poulsen conjecture for intersection of balls in spaces of constant curvature. So we are searching for a method which is not predominantly Euclidean, such as the Brun-Minkowski inequality. Okay, so I will skip here the details of this result and move on to the idea which leads us to the solution of this. And the other reason why I want to come up with this, because it is, after all, a very elementary thing that helped me out a great deal. I call them Arduous sets, and let me introduce Arduous sets. So the setting is we are in a d-dimensional Euclidean or hyperbolic or spherical space. We, of course, know that there is this geodesic distance, which I label in this way. So MD stands for either Euclidean d-space or hyperbolic d-space or spherical d-space. There is this notation R+, which I need to explain a bit. So if the curvature of space is non-positive, then, in other words, if we look at the Euclidean or hyperbolic case, then R+ refers to the set of positive real numbers. If it happens to be the spherical case, then R+ refers to this half-open interval. So my radii that I will choose will be chosen from R+. Okay? So we will take a set X in our d-dimensional space of constant curvature and choose a radius. So if it is Euclidean or hyperbolic, there is no restriction on small r. It can be any positive real number. If it is spherical, then small r cannot be larger than pi over 2. In this way, we know that the balls that we choose are convex sets. And then if I take a set X, I introduce the R dual of the set X as an intersection of balls centered at the points of X having radius R. So the procedure is very simple. Small r is given, capital X is given, and we take this set XR and call it R dual of X, and this is the intersection of balls of radius R centered at X. Now, what do we know about these R dual sets? Well, you know, it's very probably intuitively clear that this lies very closely to spherical polars or simply polar sets in Euclidean case. So when you look at the properties that we have for R duals, such as this one here, or the monotonicity that if X is a subset of Y, then YR is a subset XR, this reminds us to polarity. And so what I want to do, I want to sort of adventure this direction and say something volumetric on these R duals. A good starting point, and that was the motivation for me, is a recent theorem of Gao, Hook, and Schneider in spherical space, which you can see here phrased. So for any convex body of given volume in the spherical D space, the volume of the spherical polar body becomes maximal if the convex body is a ball. This is an inequality or a theorem which was published in this paper and which often is referred to as a Blaschke-Santalo type inequality in spherical space. So that's exactly what I'm generalizing here. Theorem 1 as a Blaschke-Santalo type inequality for these R dual sets. So it is phrased as follows. We take a compact set of some volume, and then we choose a radius. And then the inequality says that if we take a ball whose volume is equal to the volume of our set, compact set, then the R duals behave nicely. Then the R dual of our compact set A has volume at most as large as the R dual of the ball. So that's the inequality. And this is a generalization of the Gao-Hook-Schneider theorem, namely when the space of constant curvature is spherical and the radius is pi over 2, then the R dual of our set is the polar, spherical polar of that. Now, the proof is another lucky circumstance because their proof in spherical space is an application of this method which is called two-point symmetrization, but it is applied indirectly to the polar set. So it's not applied directly to the set that we start with. It's about the polar set, it's applied to that. Here, it turns out that one can, that's where I learned about two-point symmetrization, actually. It's a nice method, and I can briefly go through the proof, how I prove this theorem. It will make use of two-point symmetrization. This is a method that can be used to prove the isoperimetric inequality. And it's of odd nature, especially if you haven't seen this before. You would not call this a symmetrization at all. Because it starts, here's the definition, and let me explain what two-point symmetrization is. So we take an oriented hyperplane in D space, in this space of constant curvature, d-dimensional space. Orientation means that it has it bounds two closed half spaces. One we label by H plus, the other by H minus. And then we will need reflection about H. Sigma sub H denotes the reflection about the hyperplane H here. And then we start with a set K. So here's K. And we two-point symmetrize K as follows. Here's the formula for the two-point symmetrization of K. We take the intersection of K with its reflected image. This is an H-symmetric set here in the middle. And then we take the union of this set with the intersection of the union of K and its reflection with the upper half plane. So the shaded set is the two-point symmetrization of the K that I have here in the diagram. You know, it doesn't look more symmetric than it was. Still, this is a name that is used in the literature, two-point symmetrization. Often it is called also polarization. Other names are also here. But there is a very good property of this symmetrization which comes forward when you generate a disjoint decomposition of the two-point symmetrization of K. Namely, you could take the H-symmetric core of K, so you intersect K with its symmetric image. You reflect K about H and then take the intersection of these two sets. This is the H-symmetric core. And then you take two other sets here. You take the part of K which lies in H plus and does not belong to the H-symmetric core. This is this little hat thing here. Sorry. And then you take the other part, which is K, which is the part of K which lies in H minus and doesn't belong to the symmetric core, and reflect this about H. In this way, we manage to dissect the two-point symmetrization of K into three disjoint sets. And in this way, we see it's volume preserved. So one good thing about this two-point symmetrization, that this is volume preserving. Now, this is what we are going to use here for the proof of that Blaschke-Sandalo type volumetric inequality. We do this, we need two lemmas here. In order to state these lemmas, it's a good idea to introduce some convexity here. What we do, we just say that if we have a set K, then its R-convex hole is the intersection of bolts of radii R containing K. Okay, so this is what we call R-convex hole, and the set K is R-convex if it is equal to its R-convex hole. Now this is a good thing, a useful thing, because when you look at an arbitrary set K and its R-dual set, it is the same as the R-dual set of its R-convex hole. This is a little lemma, which is not difficult to prove at all. And the key for the proof of our theorem, you see here. This is lemma 5. This says why two-point symmetrization is a good idea to bring forward here. Namely, I have a K, and its R-dual is there with some volume. Now I want to do something to K such that I increase the volume of the R-dual. How do I go about this? I take the two-point symmetrization of K. Well, I can take also its R-convex hole and take the R-dual. It turns out that this contains the two-point symmetrization of the R-dual of K. Since the two-point symmetrization preserves volume, this set has the same volume as the R-dual of K. So in this way, we see that, well, this new set has a volume at least as large as the R-dual of K. So this is the heart of the matter here. Two-point symmetrization will help me to increase volume, and we deploy two-point symmetrization. I don't go into details here. What I really want to do is just to say that the rest of the proof is more or less standard. We will investigate the extremal bodies for which the R dual has maximum volume, and we observe with the help of this lemma, this key lemma, that the extremal family is in fact invariant under 2-point symmetrization. And the rest then follows. So this is the main tool here, the 2-point symmetrization. Now, how do I use this for Kneser-Poulsen? This is the other part. So now we look at uniform contractions in d-dimensional spaces of constant curvature, introduce them in the same fashion as we did in the Euclidean case. So there is this lambda separating value in the middle. And then the idea is to come up with a theorem, what you see here. I really just want to focus on the middle part here and state the spherical theorem, because this is the theorem that I was mainly interested in due to the special theorem on closed hemispheres. So this middle part here is a spherical result. So we have here a point configuration Q, which is going to be a uniform contraction of the point configuration P. We will draw both of radii delta around these points. So that explains this. That explains this. This part here. This part here. So P delta. I'm looking at the delta dual set of P and the delta dual set of Q. These are intersections of both of radii delta, and we want to show that if Q is a uniform contraction of P, then the volume of Q delta is larger than the volume of P delta. But we have to be careful. Delta we choose accordingly. So what we do here, we have lambda as the separating value for uniform contraction, and we have this lambda here, and we have also delta. Delta is going to be the radii of the bores. So delta can be anything between 0 and pi over 2. As soon as we choose delta, we choose lambda accordingly. So lambda should be smaller than this value here. So after that, we have delta and lambda, and we take a point configuration Q that is a uniform contraction of P with separating value lambda. And if n is sufficiently large, the number of points is sufficiently large, and here you see this does not depend on neither lambda or mu, this depends on the dimension only, then the Kneser-Poulsen result holds. So this is the theorem that I prove based on this Blaschke-Santalo type, volumetric result. How much time do I have here? Maybe. Oh, okay. Yeah. I will not use it then completely. I just want to give some brief sort of description what we are going to do. The usefulness of the notion of uniform contraction lies in the fact that one can approach this Kneser-Poulsen conjecture in the following sort of naive but actually very effective way. Namely, when we look at the point configuration Q, we have the restriction that the pairwise distances are upper bounded by lambda. So we draw balls around the QIs with radius delta, and we take their intersection, but we have a restriction. The diameter of the center points cannot be larger than lambda. So that means that we can ask for the minimum volume of the intersection. So there is a mean problem involved here. Depending on delta, lambda, and n, we can search for the minimum volume intersection of bores of radii delta centered at the point configuration Q, where the diameter is upper bounded by lambda. It's a meaningful extrema problem. At the same time, there is another meaningful extrema problem here, namely the point configuration P has the condition that the shortest non-zero distance is lower bounded by lambda. So the points are not very close to each other. Therefore, when you look at the intersection of both of radii delta, there should be a maximum volume thing here, and that's the max problem. So we have a min problem and the max problem, and in order to squeeze out the Kneser-Poulsen result, we just have to show that the mean is at least as large as the max. That's the naive strategy, and that's what one needs to execute here. And the lower bounding the mean as something traditionally available, it goes back to the Jung theorem. Upper bounding max is the new part. That's where we use this Blaschke-Santelot type volumetric inequality for RUS. Thank you. I stop here.